So the third and final part of this section, now that you've seen a more detailed example that uses parallel streams and splitterators and so on, we're going to kind of take a step back and talk about when to use parallel streams, which is a good thing to know, and also when not to use parallel streams, because it's not intended for use in every possible circumstance. So let's start first by discussing when you should use these things. Well, just a restatement of something that hopefully is becoming obvious by now. A parallel program always does more work than a non-parallel program. Why is that, you might ask? Well, unlike a sequential program, a non-parallel program, we've got to start by breaking up the problem, in other words, the input, into chunks. We've got to partition it somehow. Whereas a sequential program just begins, right? It just starts to run. So we have to figure out a way to slice things and split them up. Then we need to do the processing, which of course has to be done with either the sequential part or the parallel part. So those things are more or less the same. In fact, you can see that the sequential code is often identical to the parallel code. It just happens to work in the parallel version on a chunk of the input as opposed to the whole thing. And then the final thing we need to do is combine all the results back together again, which is, again, something very easy in a sequential program, because typically in a sequential program, you apply the accumulate pattern where you just do the work sequentially and you update some field or some variable with the result or results as it finishes. Whereas in the parallel approach, you've worked on all these things in parallel, and now you have to find some way to merge them all back together again. So clearly, the parallel program is going to do more work, but it's also going to end up getting a win if conditions are right. It kind of reminds me, anybody here ever played the game of life? Remember the game of life where you have like little cars and you spin the wheel and you go around? Remember when you start out the game, you have sort of two choices. You can either go to work or you can go to college. And if you go to college, it typically takes a little bit longer to get started. But when you go to college, then all the rest of the game, you get other benefits, right? If you pass payday or whatever, you've got a better paying job or whatever. So the point is that it takes a little bit longer to get started, but you get a bigger win if you play your cards right or you spin the wheel right. So that's kind of the same idea here. So the point is that streams are useful in some, but by no means all conditions. So you've got to figure out the right ways to use it and when to use it. Oh, and by the way, this link here has some really nice discussions, some guidance on when to use parallel streams. And I'm going to summarize some of the key points in the slides, but take a look at that if you want to know even more about this. So you should use parallel streams when the behaviors, in other words, the processing that you're doing, meet certain conditions or certain properties. The first of which is, are they embarrassingly parallel, right? So that's one of the key themes. If you have little or no dependencies on the processing, that's a good time to use them. So are the input behaviors independent? That's just a fancy way of saying, are they embarrassingly parallel? So clearly things like searching for phrases in a list of input strings meets that criteria. So that's a good example. And you can see there's a lot of those examples in our different implementations we have of our SearchStreamGang. And in fact, the most aggressive one, the so we have search with parallel streams phrases, which searches for chunks of input in parallel. We have search with parallel stream inputs, which searches for input in parallel. And then we have our splitterator, which searches for everything in parallel. So once again, we can kind of get the most aggressive approach that combines them all. But in all those cases, they're all done in ways that are independent. So those types of problems work really well. Another thing to look for are problems where the work you're doing at any given point in time is computationally intensive. So you're doing, computing an FFT or, the nth value of pi or the nth factorial or whatever, right? You're doing some long-running computation. So if what you're doing takes a long time to run, that's also a good candidate for parallel processing. Yet another condition or another property to look for is that you've got a lot of elements to split efficiently. So you've got a whole bunch of things that you need to work on and do them in parallel, right? You're not just doing sort of one thing. So those are the conditions to think about. And it turns out that when you have these properties, computationally expensive and applied to any elements, there's actually a model, a mathematical model that you should apply as a heuristic to help give you some guidance as to whether it's worthwhile doing the parallel computing approach. And if you take a look at this link here, it's a presentation by Brian Getz, who's a chief architect for Java. And he talks about the so-called NQ model. And the NQ model basically says, figure out what n is, where n is the number of data elements to process per thread or per core. Figure out what q is, which is a quantification of how CPU intensive the processing is on each element. And if you multiply n times q, and the value is high, where he says high is 10,000 or above, and that's, of course, just a heuristic, right? That's a guess. It's an educated guess. He says if it's roughly 10,000 or above, then parallel streams is probably worth it. If it's much below that, then it's probably not worth it. So that's his suggestion. So for something like our SearchStreamGang, that was one where as n got bigger, parallelism was a bigger win, right? If we only searched, one act from one play and one phrase, parallelism is probably way overkill. But if we're going to search all the works of Shakespeare with lots of phrases and so on, that's probably a win. So if n is bigger or q is higher, and or q is higher, then we're going to get a win. So that's the NQ model to think about. Another obvious one is, do you have multiple cores? If you don't have many cores, then parallel streams are just going to make things slower. If you have only one core on your machine, probably putting parallel stream will make things run slower, because now you're going to partition and you've got to join, but there was nothing to actually make it run in parallel. So there was no win for doing that at all. So under the right conditions, you get a big speed up, and I've shown you some examples here where we do get that. Even on a relatively modest multi-core machine, right? 4 cores isn't a whole heck of a lot compared to what's available now on high-end servers. All right, so that's when to use streams. There's also the issue of when not to use streams. So it turns out that there's certain programs where you should not use streams. You'll just drive yourself crazy doing it, and it won't be a win. So don't get in the habit of just putting parallel stream everywhere, although it can be useful sometimes to try it out to see that, and it's really easy to make the change. So one condition where parallel streams are not a good idea is if the input source is either very expensive to split or doesn't split evenly. So if it doesn't split evenly, or if it takes a lot of time to split it evenly, then it's not going to be a win. And to prove all this, you should take a look at this link here in my GitHub repository, which shows this example program. And what this example program does is it basically creates a list of all the words in the works of Shakespeare. And so we have two different things. We have an array representation of all the words in Shakespeare, and we have a linked list representation of all the words in Shakespeare, right? So two different representations of the words of Shakespeare, of all the words in Shakespeare. And then what we're going to do is we're going to go ahead and we're going to count the number of words, and we're going to count the number of words in parallel for the array version, and we're going to count the list of words of all the works of Shakespeare in parallel for the linked list version. And if you were to do that, or when you do that, you'll see that the array list version is way, way, way faster than the linked list version. And the reason for that is, we'll go into more detail shortly, the linked list approach splits very poorly, because trying to figure out where the halfway point is requires you to traverse half the list, right? You can't just take the beginning and the end, multiply, and then divide by, or add them up and divide by 2, right? You can't just find the middle easily. You have to traverse through the list to find where the middle is. So obviously that's going to be a much more expensive operation. Even to do something as simple as counting, right? Here's what the array list splitterator looks like. This should look very familiar to you guys by now, because this is pretty much what you had to write for your splitterator for your array class. So here's try split. As you can see, it basically goes ahead and takes the low plus the high and divides it by 2, and that gets the midpoint, and then it goes ahead and splits things up. So super fast, splits evenly every time, doesn't require any looking at the input source, so it's constant time, and splits evenly. In contrast, here is the linked list version. And the linked list version doesn't even try to split things in half, what it does is it goes through a chunk at a time, or a batch at a time, and it creates an array, and it copies a chunk of the elements into the array. But the array is not necessarily meant to be like half the size of the input. It starts with a certain value and keeps growing each time. And so it'll make this array, it'll copy the elements into the array, and then it'll go ahead and say, take that chunk and turn that into a splitterator, please, by calling a library routine called splitterators.splitterator. Splitterators is a static utility class in Java with the splitterator method, and it splits things up into these little chunks. But you'll end up creating a lot of these things. And so it's not split evenly. And it takes a fair amount of time to do, because we have to go through all this processing to figure out how to even copy things into this new chunk. So it doesn't optimize nearly as well as the array splitterator. So those are the two different implementations there. So the point there is, if you can't split your input up into, if you can't split the input evenly or efficiently, parallel streams is probably not going to be a win. We'll give you a little bit more twist to that in a second. Another issue here is if the startup costs of parallelism are higher than the amount of win you get by running things in parallel. So if either of those things, or if that's the case, you're also not going to get a win. So here's another example from my GitHub repository. And what this is doing is it's computing factorials, right? So we're going to basically go ahead and compute n factorial in parallel and n factorial sequentially. And if you look carefully here at these two pieces of code, the only real difference between them is that this one says dot parallel and this one doesn't. Otherwise, they're pretty much identical. Well, if you give a value of n for which you want the nth factorial computed, and that value is relatively small, like, I don't know, 20 or less, which, by the way, is about as big as you can get without overflowing the size of a long, you'll find out that the parallel version actually runs slower than the sequential version. Why is that? Because it takes a while to split the input up into chunks and then merge them all back together again. And that time is better spent for small n just doing the factorial computation. So you'd actually have to give a fairly large value of n for n factorial before you'd get a win by doing the parallel computation. Now, this, of course, is why this test program uses big integer. And if you use big integer, then you can do n factorial where n is ridiculously large, and you'll get a gigantic result, and you'll start to see a break-even point where the parallel version is faster. And you would probably expect that to be when n times q equals 10,000-ish or so, right, using the n times q model. Another related, sort of the inverse issue is what happens when it takes a while to combine the partial results. Does anybody know what that is? What's that? Traffic jam, right? You're trying to merge a bunch of autos and bikes and buses and vans together. You're trying to merge something. This weekend we went to the Pilgrimage concert down in Franklin, where they had Justin Timberlake play on Saturday night. I'm not a big Justin Timberlake fan, but I have to give him credit. He's a great performer. But he also is a major draw. And so there were like 20,000 people at this little concert venue, which was a great concert venue, but it was absolutely not set up for large amounts of traffic. So after the show, we had to wait like an hour and a half to get out of the parking lot because you couldn't get the traffic merged in any efficient way. So it actually probably looked quite a bit like this. So combining partial results is costly. So let's take a look at an example. You can see the example here. So certain things combine very nicely, right? So if you were going to take strings and concatenate them together, that can be done very efficiently. If you're going to take partial results that are sets, combining those things, combining two sets together into a bigger merge set is actually fairly expensive. Why is that, by the way? Why does it take a while to merge sets together? Unique? Sure. So one thing is it has to make sure that it doesn't allow duplicates, but there's another reason why it takes a while. What's the reason from an asymptotic time complexity point of view? how long does it take to take a string and append another string at the end of it? It might take constant time, right? You might just, if you have a big enough buffer already or you have a clever implementation, you just tack it onto the end, right? It takes very little time at all. If you have a set with n elements in it and you want to merge that into another set of n elements, how long is it going to take to do that merge? What's that? Right, but what's the asymptotic time complexity? So, all right, so we have n elements that are already in a set, and we want to, copy them into another set of n elements. How long is that going to take, roughly? How long will it take? I think you were on the right track. How long will it take one element from the first set and put it into the second set? Did you guys forget everything you learned in data structures? If you have an ordered set, all right, let me make it easier. We've got a balanced binary tree. That's how the ordered set would be implemented. So what's the property of a balanced binary tree? What does it take to do any operation on a balanced binary tree? Log n. All right, so each element takes log n. I've got n of those elements. I've got to put them in the other set. How long will that take? N log n, right? So it's basically equivalent to sorting. So it's going to take n log n time to merge the sets together. So if you combine partial sets into a final set, it's going to take a fair amount of time to do that. So this is an example where we go ahead and compute the number of unique words in Shakespeare by starting out with all the words, and then we collect them together into a tree set. And if you do that in parallel, if you run the program, you'll see it actually is a non-trivial thing to do. It takes a fair amount of time. Now, this could still be a win if you do something else that takes a while to run, right? So the cost of merging the sets could be amortized or relaxed or tolerated, probably a better term. You could tolerate the merging if you're also doing something else that's computationally intensive along the way. So if you're doing something really complicated to the sets as opposed to just merging them, then you could still get a win from parallelism. So if Q is really high, the fact that there's a fair amount of overhead for merging will still give you a win for parallelism. But you typically don't know that, right off the bat. You'd have to do some experimentation. Another interesting dimension to this is some Java 8 features don't exploit parallelism very well. And this is really interesting to look at this and understand what happens. So you can take a look at my program here to see more about this. But here are two programs that both do essentially the same thing. And what they're doing is they are going through some, n numbers. Let's see, I guess it's, we start out with some, here we go, number. We're going to go find the first n even numbers and compute their square root. So that's the requirement. The requirement for this program is compute the square root of the first n even numbers. Okay, and there's a couple ways to do that. Here's one way to do it. The first way is to use what's called an infinite stream generator called iterate. And iterate will start at 2, and it'll generate a stream infinitely that adds 1 to the element that was there before. So it's going to be 2, 3, 4, 5, 6. It will just generate that stream infinitely. And we're going to do this in parallel. And we're going to filter out the even numbered values. And we're going to go up to 100. Or sorry, we're going to go up to n. Let's say n is 100. And we're going to find the square root of that. And we're going to collect all the results into a list. So that's what this program is doing. And this will take a really, really, really long time to run. And the reason for this is that iterate and limit both split and parallelize very poorly. There's a lot of overhead. And if you want to convince yourself of this, try running the program and you'll see. Here's an alternative way of doing this that is way faster. And this is going to use the range method. So range is another method you can use on a stream, in this case a stream of longs. And what this is going to do is it's going to go from number times 2 plus 1, right? So if we want to find the first n even numbers, we just double the amount of things we're looking for, and then we search for the even numbers. So we run this in parallel, we filter out the even numbers, we get their square roots, we collect that to a list. This runs way faster, and the reason is that range works on an array representation, which splits nicely, and efficiently and runs really, really, really well in parallel. So this is much, much faster than the approach that's shown up here. And of course, the other reason why you might not get a win from a stream is that you only got one core, or you have a small number of cores, so you're not really getting a win. Obviously, over time, that's becoming less and less likely because it's getting harder and harder to buy computers that only have one core, which is great. If you know how to program them, of course. Otherwise, they just become more expensive ways of doing sequential computation. All right, so that is the end of that